Okay, last time we talked about the average velocity of an ideal gas. From the velocity, of course, we can get the kinetic energy. The average kinetic energy is equal to m and that according to what we had is m over 2 times 3 RT over total mass. Which is equal to 3 over 2 RT over the total number of particles. So it's equal to 3/2 of kT. The particle has three directions: Vx, Vy, Vz. The average of Vx squared, average of Vy squared, average of Vz squared are the same. So each degree of freedom of motion gives average energy of 1/2 kT. It is equal to about 4 times 10 to the minus 21 joules at 300 degree K. This is of course an important concept, and it's one of the reasons that people in the 19th century began to believe the kinetic theory, that indeed the particle motions contribute to the mass, to the energy of the system. And since the energy can be measured in various ways, so this became one of the important hints that the atomic theory or the kinetic theory is valid. But it was not universally accepted. There were strong oppositions to this idea. If a gas consists of many particles, and if the particles are infinitesimal in size and they do not hit each other, if they are very small, they just go past each other when they get close. If that were the case, then a particle would keep on moving in a straight line until it hits the wall. But that's not the actual fact. Actually, the atoms can be thought of as interacting balls. The idealized one is to think of them as if they were ping pong balls, and each ping pong ball has a diameter. So when two ping pong balls come too close to each other, they would hit each other and they would bounce off. As a consequence, the air molecules in bouncing around would hit each other. Mean free path means, on the average, the distance between two collisions of any single atom. Some molecules or atoms would hit, if it happens to be close to two other atoms. It might hit the first one and then immediately hit the second one. But others may be traveling in a region where there are few other atoms. Then it will travel a long distance without hitting. 3 pass means the distance between 2 hits. Mean free pass means the average distance, the average of the free pass. And there's a formula given in the book, which I shall only copy down without explaining how it's this is about a monatomic gas. For example, helium or neon. These are single atom gases, not oxygen. Oxygen forms a molecule, becomes O2, and O2 is like a dumbbell. It's 一个哑铃. This formula is supposed to be valid for monatomic gases, and rho is the density of atoms per unit volume, and d is the diameter. This formula is 20-25. This formula is supposed to be valid for hard spheres, like ping pong balls. But actually atoms are not ping pong balls. The atoms already have a force on each other even at a distance, and it's a rather complicated thing. So d in that case is the approximate distance between 2 atoms when there begins a strong force between the 2. At the 1 atmosphere, at 300 degrees Kelvin, lambda is approximately 10 to the minus 7 meters. The diameter of atom is approximately 2 times is approximately 2 times 10 to the minus 10 meters. So you see that the mean free path is rather large compared to the diameters. So you can think of a lot of ping pong balls bouncing around. The average distance between them is quite large, and they would bounce around and on the average hit each other at 10 to the minus 7 meters, which is 500 times more than the diameter. So in general, most of the time it's not hitting, but once in a while it would hit. This lambda, of course, becomes much smaller if the density is smaller. If the density is smaller, in the denominator, a lambda would become larger. So if you go to high atmospheres where the density of air becomes less, then the mean free path becomes much longer. Well, that's of course very natural. There are fewer obstacles to hit, so therefore the mean free path becomes longer. we had last time and earlier today talk about the average velocity of molecules and atoms. But of course, not all atoms or molecules in a gas have exactly that mass, have exactly that velocity. Some of them have higher velocities, other of them has lower velocities. And that distribution is called Maxwellian distribution. It's just the number of atoms, the number of molecules with V in dV. Let's understand this formula. The number of molecules with V in dV, that means the V is in Vx plus dV, V to, that means V in Vx to Vx plus dVx, Vy to Vy plus dVy. This is a small interval. 一个小的 Vx 的阶段，从 Vx 到 dVx，Vy 上 Vz 是这样。在这一个小的 region 之中，这个 atom 的数目是等于 dVx、dVy、dVz 乘上一个 exponential function， 前面乘上一个 numerical constant。这个 exponential function 呢是负的。 底下是 kT， 上头是1/2个 mv squared。这个当然又可以写成这个通常写成这样，就是把前面这个东西写成 PV， 所以 P of V 就等于 constant 乘上 exponential。 因为这个 v squared 是 vx squared 加 vy squared 加 vz squared， 所以我可以把它写成三项乘起来。exponential 三个 exponential 乘起来就把它的 exponent 加起来就完了，所以就变成这样。这个有时候又把它写成这三项 separately 写开。这个 constant 是怎么 determine 呢？ integral pz pv dv 是这个 v 是3个 minus infinity minus infinity minus infinity。我不应该叫 number probability。这个 PV 是 probability， 所以这 probability 是 such that 这整个所有的 possibility integral 就等于1。大家都了解不了解 ？OK， 那现在 the way we wrote it is dvx, dvy, dvz. But how about the square root of v squared? 那么这个呢是你可以这样写法我现在在 v space 是 3 dimensional。Consider v space vx, vy, vz 是相乘。现在我问说是在这个一圈里头 between v and v plus dv 有多少 volume dvx, dvy, dvz 就是在 v space 里头的 volume。那么 between v and the volume in dv space 是等于什么呢？等于这个 area of 这个 sphere。area of sphere 是 4， 这个 distance 是 v， 是 4 pi v squared， 这是球面的面积乘上 thickness 是 dv。所以你刚才那个 PV dV， 这是这 probability。in V for V between V and V plus dV， 这个 probability 呢，就等于刚才这个 area 4 pi V square dV 乘上这个 probability 乘上 exponential minus 1/2 mv squared over k， 乘上那 constant。这就是这一部分，就是我刚才写的，这是它的 area， 所以你把这都乘出来，就变成另外一个 constant， 乘上 v square， 乘上 e to the minus 1/2 mv square over kt dv。这个 probability 有时候写成 pv dv， 这不一样的地方是，这个是 speed 是 one dimension 的，刚才写的那个是3个 dimension， 这两个是一回事情。不一样的是3个 dimension 的一个 dimension 时候，这有个 v squared， 在3个 dimension 时候没有那 v squared。为什么有这个 difference 呢？就是刚才讲的那个球面积是 4 pi v square， 所以从 dvx、dvy、dvz 变成 dv 的时候，要出一个4 pi v square。这个方面呢是2027。我如果画出来，这是 v， 这是 p of v。那么在 v 小的时候呢，这个是1。在 v 小的时候，这个 exponential 是1，所以就是 v squared， 所以是这样。这个地方是个 parabola， 然后涨上来，然后到 v 非常之大的时候呢，这个虽然很大 ，but the exponential would damp down. Exponential minus v squared goes down much faster than v squared. So therefore, this whole thing becomes 0.你们不要这个被负了，说是这儿是很小，这并不代表 small v 是很小。这个 v 所以少，是因为这个4 pi v squared， 是因为就是如果你拿这个 v 来看，在 v 等于0的时候是 maximum， 就是在 3 dimension 里头 ，if you take those 3 dimensions。This distribution is this exponential. So the maximum probability is at the origin. 就是不动的 velocity 的是 probability 最大，越远的时候就 die down， 是一个包，一个土包。可是这个地方为什么变成一个 v square 呢？是因为非常小的 v， 它那个 area 小，没有那么多 small v 的那个面积小。这一点你们得要了解。那么这个 distribution 有一个特点，这个特点就是代表 there exists even though with a very small probability very large velocities。这个我们这空气里头动来动去的有很快的。那么这个 is also true in a liquid. So in water, the molecules are moving around, and there are some that's moving very fast, and those that move very fast are likely to escape. So when you have evaporation, the particles that come, the molecules that are evaporated, in general have larger average velocity than the molecules which have not escaped. Those that are too slow would bounce back. That's the reason why you need to heat it, because the average energy in the gaseous state is larger than the average energy in the liquid state. So to keep the temperature fixed, you need to supply energy. That's why there's energy of evaporation, and that's also true for the heat of melting. When ice melts into water, the average energy of the motion of the atoms of the molecules in ice is less than those in the liquid. So therefore you need to supply heat in order to make the transformation. We are now going to talk about the monatomic gas. Now, what has the internal energy? Each degree of freedom has a 1/2. It has 3 degrees of freedom. So the average energy per particle is this, and if you have n molecules, so that's the total energy, and that's equal to 3/2 is n divided by n divided by Na. Na is the Avogadro's number. The total number divided by the Avogadro's number, that means the number of moles. NaKT. NaK is R, so it's RT. So the total kinetic energy is dependent, in this case, only on the temperature and not on the volume. What we are talking about is the ideal monatomic gas. We have a fixed number of molecules. If you have a fixed number of, let's say, hydrogen or helium, not hydrogen, helium. Helium is monatomic. You can still have two additional choices. You can put it at a certain temperature, and you can, at that temperature, you can make it large or small by changing the pressure. So that system has two variables, T and V. But for an ideal monatomic gas, the energy is only a function of T and not of V. This makes a monatomic gas very simple. Makes ideal monatomic gas very simple. No real gas is exactly like this. If you take helium, it's almost a ideal monatomic gas, but not exactly. There are various reasons for this. Most importantly is because they are collisions. And in our derivation earlier, when we derived the pressure relations with the velocity, we assume that the particle moves around and does not hit. So therefore, we said that in 1 unit of time it goes Vx in the x direction, and that divided by 2L, L in the box length, gives you the number of hits. That number of hits of the wall. That assumes that there's no collision between the atoms, which is in general not true. That means that for a non-ideal gas, this formula is not correct. That formula is not correct, and therefore this formula is not correct. But let us persist with this ideal monatomic gas, because for real gases at the usual volumes, the mean free path is very long, so you can neglect it. In that case, the specific heat per unit volume, CV is the specific heat per unit volume, is the increase of energy per unit time, per unit temperature increase, so it's equal to 3 to nR for 1 mole. And it's equal to 12.5 joules per mole per degree. Already in the 19th century, people know that this is not true for a diatomic gas. For example, for nitrogen. This is true approximately at relatively dilute situation. But for diatomic gases, experimentally it was found that CV is approximately 5 halves, like nitrogen. And for example, ammonium, CV is approximately equal to 6 halves. So why is this so? The reason is because there are more energies than the average kinetic energy for these cases. If the molecule is a dumbbell, 是一个哑铃, then it not only can it move, and the 3 degrees of freedom of motion each would contribute per atom, per molecule, 1/2 of kT. But it's like this, it can also flip around this way. Now, this kind of a motion has 2 degrees of freedom. Namely, if you have a rod this way, to describe its position, you need to specify, for example, theta and phi. So you have 2 degrees of freedom, and it can move in each degree of freedom. So, observing the experimental results, Maxwell formulated the principle of equidistribution of energy. He said that for each degree of freedom, there is an average energy of 1/2 kT. 1/2 kT for each kinetic motion, for each linear motion. But for each rotational motion, there's also 1/2 of kT. So 3/2 of kT plus 2 times 1/2 of kT gives the 5/2 of kT. So there's an explanation of this. For NH4, it has an additional degree of freedom, namely it can rotate around this direction. This is nitrogen. It has 3 legs and 1 leg this way. It can still rotate this. So it has 3 degrees of rotation. It can move this way, but it can also rotate along the axis. So in that case, there are 6 degrees of freedom. So it's 6/2 of kT. And this is in very good agreement with the experiment for dilute cases. But when one studies the problem more in detail, this was all in 19th century. 发现了，it's not that simple。大家研究这个 CV over R for hydrogen atom。根据我们刚才讲，应该是 5 halves。因为它有3个 linear motion，each of them gives one half，然后有一个 rotation 是一个棒子一样的，这个棒子有2个 degree， 所以是5 halves。是书上画出来这个 experimental 的图，这图是假如你这是100度 K， 这是 logarithmic 1000度 K， 这是10000度 K， 这边画 CV over R。根据那个 theory 是应该在这儿 2.5。实验呢是果然是有一段是 2.5。它变成3段，中间是有一段是 2.5，so everybody's happy。不过呢，你当温度低的时候呢，它只有 1.5， 再高的话呢到3，所以这问题是what's going on？ 这个 this was a great puzzlement. This is not only true of hydrogen, it's true of all gases. And furthermore, it's not only true of gas, it's also true of solids, because there are also theories about the vibrations in the solid. And there's something called the Dulong-Petit law, which is almost true, but there are always deviations. So the question is, something is peculiar. And that's the first hint of quantum theory, the hint of quantum phenomena. After quantum mechanics was developed, one understands not only qualitatively, quantitatively this curve, but the details are very complicated. So we can only talk about the qualitative feature today. In this region, we have 5 degrees of freedom, correctly. In this region, there's one more additional degree of freedom. There's no rotation like this, but the dumbbell could vibrate. When we talk about the 5 degrees of freedom, we regard the hydrogen atom as a fixed dumbbell. But if the temperature is high enough, that means that there's more. When the temperature is high, every degree of freedom wants to move or wants to agitate. So this vibrational degree of freedom also comes into the picture. And when that is fully developed, it increases this 1 degree of freedom. So this addition due to vibration. What that means is 在 5 half 的时候，那个 degree of freedom frozen， 所以有一个 concept of frozen degrees of freedom。In other words， 在这儿的时候，这个 vibration 的 degree 是 stuck 住了，它没有够多的力量来excite 它，所以它是 frozen as if 它是 rigid。可是到了够多的温度的时候，它也 come into picture。但 once it come into the picture, eventually 就变成了 additional degree of freedom， 所以又加了一个1/2 kT。那么 that's also true here。在这儿的话呢，是只有3个 degrees of freedom， 所以是2/3。那的意思就是说那个东西不转。这个当时不懂，就是你看到这个以后呢，就知道是有一个 phenomena， 它可以 freeze， 可是不懂为什么一个东西在这儿可以 freeze。那么这个的最后是 quantum mechanics 出来以后才懂。这个 freeze 这句话，有语病。它最重要的就是说那个 degree of freedom 是 stuck 住了，它不能动，要到够多的 energy 才能够把它excite 出来。所以像这样子的图，等到懂了 quantum mechanics 以后，你就完全懂了，而且可以 quantitatively calculate 整个的 curve。这当然就是20世纪一个 great achievement。Does everybody understand what I said qualitatively? Actually, it involves both why there was original 金义 and 后来怎么这个金义后来被了解了。In fact, before it was understood, this was considered one of the greater puzzles, because clearly physics says something which is correct. The 3 halves, the 5 halves, all beautifully agree. Besides, all gases have similar phenomena. But yet one did not understand how it can do something like this. That's one of the great puzzlement around the beginning of the 20th century. Another puzzlement was the Michelson-Morley experiment about the electrodynamics of matter. There are multiple puzzles. So, in around the beginning of the 20th century, there was the danger that the whole of physics would collapse, because there were too many things which everybody did not understand, while there are many things that everybody understood. And this mixture of things understandable and things not understandable created a crisis. And 100 years ago, in 1905, Einstein came along and showed in 1 year he solved many of these problems. Not this one, quantum physics, he made a great contribution in 1905, but the finer understanding of quantum mechanics had to wait another 20 years. Now we come back to 20-8. Specific heat at constant T.现在我们 consider 1 mole of gas. 不管它是monatomic 或者不 monatomic， 不过是我们 consider 是个 idea， 就是那 PV 的 formula 是对的。那么我们现在要at a constant pressure. This is an isotherm. 比如说我从这儿让它固定的 temperature 让它压缩。可是呢，我可以让它这样做，让它 constant pressure。如果这样走的话呢，就是 at constant pressure 让它的 volume 增加，那么它的 temperature 也在增加，因为这个 curve 的 temperature 比这个 curve 的 temperature 大，所以一个 isotherm 一个constant pressure 的specific heat 是我们要算的。那么我们知道first law of thermodynamics 是说total internal energy 的 increase 是等于 heat input 减掉它所做的 work。假如你是向这儿expand 的话，那么这 dV 是 positive 的 ，PdV 是 work done by the system on the 外界 ，therefore 它的 internal energy 要 decrease， 所以是一个负号。可是 for 一个ideal gas，one more of ideal gas， 所以这个呢是 CV dt， 就等于 dq 减去 PdV。所以呢 dq 就等于 CV dt 加上 PdV。现在我们是 pressure 是 constant， 所以 V 等于RT over P。pressure 是 constant， 所以 volume 是 proportional to T， 所以呢这就等于 CV dt 加上 R over P dt 等于CV 加上这还得乘上个 B 加上 R dt。所以 at constant pressure 这个 heat input per unit temperature increase 是等于，所以 Cp 就等于 Cv 加 R for ideal gas。我们什么地方用到了 ideal gas 呢？就是这个方面了。所以 constant pressure 它的 specific heat is larger。为什么 larger 呢？道理很简单，因为你 constant pressure 的时候，你不单要internal energy 要 increase， 而且还要做 work， 所以你必须要把你 heat 它的时候它要 expand， 它 expand 的时候它所做的 energy 你得要 heat 加进去，这就是这些方面的意思。 Let us consider an ideal gas in an insulated box. This thick wall is supposed to be completely insulating, so there's no heat input. And we can have adiabatic expansion or compression of the gas. We consider one more. Again, we write the first law. D internal is equal to dq minus pdv. 我们现在是 adiabatic， 所以 dq 等于0。左边是 cv dt， 因为我们知道 for ideal gas E internal 直 depend on T， 我们刚才讲过了。好，这个 formula 你写出来就变成 cv dt over t 加上r dv over v 等于0。所以 dt over t 加上 r over cv，r over cv 是个numerical number， 比如说是3/2或者5/2。你把两边都 integrate， 所以这就是 log of t log to the base of e dt 加上 r over cv log of v 是等于一个 constant， 我们叫它叫做 k1。这个当然就是 log of t 乘上 v to the power r over cv 等于一个 constant。所以 t 乘上 v r over cv 是等于这 exponential， 这个叫做 constant 2。可是 t 是等于什么呢？等于 pv， 我不要 t， 我要是 pv over r 是等于 t。所以 p 乘上 v of 1 plus r over cv 是等于另外一个 constant， 你把这个 r 乘过去，另外一个 constant。 1 plus r over cv 是等于 cv 加 r 等于 cp over cv， 这个平常叫做 gamma， 这个 gamma 可以 experimentally 量出来的，所以呢你就得出 p v gamma 是等于一个 constant。 For monatomic gas, Cp 是等于5/2 ，Cv 等于3/2，所以伽马等于5/3。这个我们以前已经讲过了，这是一个 isotherm， 这是 Pv 等于 constant。P 乘上 V 伽马等于 constant， 伽马是大于1的，所以它 curve 是这样。我们上回已经知道它要向这个方向走。Now we know how it， 这个是一个 constant P， 这是 constant T。比如说是我们来做一个 exercise，chapter 20， 56E。56E 是说 pressure is 1.0 atmospheres, T is 300 Kelvin. That's approximately room temperature. 是 diatomic, but no oscillation. 有 rotation, so Cv 是等于5/2，所以伽马等于7/2 divided by 5/2。等于7/5。那 PV 伽马就等于 PV 7/2 7/5，是等于 P 是一个 atmosphere 是 1.013 times 10 to the 5 Pascal 乘上 2 它的 volume volume 是22.4， at normal 1个 mole 是等于这么多，2个 mole， 它题目说是2 mole， 所以要2乘上这个的 7/2 power。This problem asks you to evaluate this international standard units, so whatever it is. 我们再做一个题目 ，exercise 17P, chapter 20. This one is something like this. You have a kind of gas. It's the same ideal gas. The statement volume is V1. 这面的 volume 是4倍子 V1， 这面的 pressure 呢等于5个atmosphere， 这面的 pressure 是1个 atmosphere。这面的 temperature 呢是300度，这面的 temperature 呢是400度。这是原来的。Then you open the valve. The pressures are not the same. So therefore, some gas is going to, it's the same gas, the same kind of ideal gas, but at different temperature and different pressures. So it would move from here to here. And it's assumed that the temperatures are kept constant. So now let's write down the final result. This is the initial. Final. Final 的话有 P1 prime. They are kept at constant temperatures. So it's assumed that the T1 prime is equal to 300 degrees. T2 prime is equal to 400 degrees. You can do that by keeping them in baths so that there's constant heat exchange, so that the temperatures are not changed. But in the end, the two pressures have to be the same. So P1 prime, P2 prime is equal to P1 prime. The question is, what is this pressure? Okay. First, let's ask how many moles of material there are. The first important thing is to know how much gas there is here and how much gas there is there. So N1 is equal to P1 V1 divided by RT1. N2, that's the number of moles in the first box. P2 V2 over RT2. 所以 N2 over N1 是等于 P2 over P1 V2 over V1 T1 over T2. P2 over P1 is 1/5. V2 over V1 is 4. T1 over T2 is 300 over 400. So that's equal to 3/5. Similarly, we can do the same for final. N1 prime is equal to P1 prime V1 prime divided by R T1 prime. N2 prime is equal to P2 prime V2 prime over R T2 prime. So N2 prime over N1 prime is equal to P2 prime over P1 prime V2 prime over V1 prime times T1 prime over T2 prime. And that's equal to P2 prime over P1 prime by definition is 1. V2 prime over V1 is 4. T1 prime over T2 prime is 300 over 400. So it's equal to 3. In other words, originally, 3/8 of the material is in here, and 5/8 is in here. No. Yes. N1 is to N2, 5 over 3. So let us call this N1 is 5x, then N2 is 3x. Because N1 over N2 is 5/3. Altogether, it's 8x. And that has to be equal to N1 prime plus N2 prime. So you have to distribute the nx moles in the two such that it becomes 3-to-1 in favor of the second one. It's clear it's 2-to-6. N1 prime is equal to 2x, N2 prime is equal to 6x. 这一来加起来是 8x, and ratio 是 1-to-3. So N1 prime is equal to 2x, N2 prime is equal to 6x. Now 我们看 P2 prime over let's calculate P1 over P1 prime. P1 V1 over P1 V1 over RT1, P1 prime V1 over RT1. V1 等于 V1 prime, T1 等于 T1 prime, so this is an identity. But that's equal to N1 over N1 prime. So it's equal to 5/2. So P1 prime 等于 2/5 of P1 等于 2 atmosphere. Any questions? Okay, I think we have now finished the first part of thermodynamics, namely chapters 19 and 20. Next time we'll embark on the second law of thermodynamics, which is the more subtle part of thermodynamics. By the middle of the 19th century, thermodynamics became well established and was recognized as a profound contribution. And so many people become very devoted to thermodynamics. But also starting from that time, Maxwell then Boltzmann, then Gibbs, began the idea that we should treat all matter as consisting of atoms and molecules. As I told you before, this idea was already in the minds of the Greek philosophers. But in the 18th and 19th centuries, because of studies of gases, there were specific ratios of masses of gases of the same volume. So it became rather obvious to some people that there is something true about the atoms, and that includes the specific heat kind of experimental or empirical results. So in the latter part of the 19th century, there was a kind of a fight between those people who push atomic theory and those people who think that thermodynamics, which consists of continuous variables, they began two kinds of schools, and the school that talks about continuous variables, nothing discrete like individual atoms, was called the school of energetics. And that consists of very important people. One of them was Mach, another one was Oswald. Oswald was a distinguished chemist who won the Nobel Prize at the beginning of the 20th century. And it happens that Mach and Oswald were both colleagues of Boltzmann, and so they had tremendous conflicts, and that conflict was believed to be part of the reason for Boltzmann's suicide in 1906. But actually, around that time, Boltzmann was already winning, or rather, the atomic theory was already winning. Because a few years before that, at the end of the 19th century, in the last decade of the 19th century, there were many new discoveries experimentally. There was the discovery of cathode ray. There was discovery of X-rays by Röntgen. There was the discovery of radioactivity, all of which, for example, there were experiments indicating that you can have, in the cathode ray tube, you can have individual particles causing scintillation on the screen, and those were individual sparks. So, for those people who kept informed about those new experimental results, it was clear that they must be atoms. So actually, in many senses, Boltzmann's school, Boltzmann's ideas about the atomic theory was winning. But nevertheless, he was depressed physiologically and also because of the tremendous dispute. So he committed suicide. Independently of Maxwell is already dead. Maxwell died rather young in 1879. So this great controversy was mostly between Boltzmann and the school of energetics. But then came along Gibbs. Gibbs was an American. He was in some sense isolated from the European physicists. In those days, America was very, very backward. In fact, the first university in the United States that was doing some research work was at Johns Hopkins University in the 1860s or 1870s. Because of that, Johns Hopkins today maintains the reputation of being a very good research university. Gibbs was at Yale. He grew up on the Yale campus and he became a professor at Yale. However, the American universities did not appreciate his talents. And since he had some money from his father, so he paid no salary at all. So he was a professor with no salary at Yale. Until Johns Hopkins had a chairman who offered him a job at Johns Hopkins with pay. So Yale had quickly to give him some salary. It was a very small salary. And there was an appointment letter by the Yale administration to Gibbs offering him a position with a salary. And that letter is kept in the Department of Physics at Yale as an important historical document. Indeed, a few years later, Gibbs wrote a book published in the early years of the 20th century, and that instantly established him as the foremost statistical mechanician. It was a beautiful book. It's a small book. If any book in physics is a bit like a poem, that is a book. That is the book. It's elegant and it's presented in a very poetic fashion. So after both Gibbs and Boltzmann died, Gibbs died in 1903, Boltzmann died in 1906. After both of them died, atomic theory gradually became one of the main thrusts of physics. Indeed, if you look at Einstein's work, Einstein was influenced by two strains of development in physics. One, electricity and magnetism, called electrodynamics. The other, statistical mechanics. He, in some sense, moved between these two, and so he changed the whole history of physics at the beginning of the 20th century, because those two were the greatest inheritance that physics had at that time from the 19th century. By the middle of the 20th century, everybody recognized that Gibbs made a profound contribution, because Maxwell was too early. Maxwell had the Maxwell distribution. We talked about that. Maxwell had the equi-distribution. We also talked about that. But the Maxwell died too early before the subsequent developments. Boltzmann carried on and had a great contribution conceptually. And so therefore today there's a formula called Boltzmann's formula, relating the concept of entropy to the concept of probability. That is a most important development in the history of physics. In fact, Boltzmann is buried in a cemetery outside of Vienna, and at his tomb there is a marble pillar with Boltzmann's formula carved on it. On top of that pillar there's a bust of Boltzmann. However, Boltzmann's reputation was eclipsed by Gibbs. The reason is because Gibbs' book is more easy to understand. Boltzmann wrote a lot, and it's somewhat confusing when you try to read it. And he did not formulate, in fact, the famous formula, which I refer to, carved on his tomb, he did not write down. It was Planck who wrote it down for him. Planck did the right thing, because if you read Boltzmann, he had all the ideas, but he did not write it down as a formula. So today, Boltzmann's most important contribution was in fact not written down as a formula by Boltzmann. That's a kind of a characteristic of Boltzmann's style of presentation. Gibbs, in contrast, had very concise formula, and these formula are now what everybody in statistical mechanics in the 20th century uses. So therefore, Gibbs became much more famous than Boltzmann. In fact, both Einstein and Bohr had said that Gibbs is the great statistical mechanics founder. Is that fair to Boltzmann? I think it depends on your viewpoint. Boltzmann had key ideas, but he did not formulate them in a understandable fashion. And Gibbs not only shared the same key ideas, he presented them in very useful form, and these forms are what all subsequent people used. But there are continuous disputes among physicists about who was the greater. In particular, Boltzmann had a student named Ehrenfest. Ehrenfest was about Einstein's age, a great friend of Einstein's. By the way, he also committed suicide in the 1930s. He and his wife, who was also a physicist, on their honeymoon in the 1910s, decided to spend their honeymoon to write a book so that his beloved teacher Boltzmann would become accepted as the great founder of statistical mechanics. The book, according to the people who read it, was very interesting. I never read it. It's very few people have really read it. Now, I think there is no doubt that most people agree that Boltzmann, in his influence, is much greater than, Gibbs in his influence is much greater than Boltzmann's. The biography that I wrote down for you, a recent biography, specifically went into this subject about the relative contributions of Boltzmann and Gibbs. The author clearly is a bit partial towards Boltzmann. But in any case, there's no doubt that Maxwell, Boltzmann, and Gibbs were the ones who had the key ideas which shaped 20th century understanding of the structure of matter. And all the 20th century technological miracles, like the semiconductor and the computer, were of course dependent on electrodynamics, depend on atomic theory, and depend on quantum mechanics. So next time we'll talk about the second law of thermodynamics, and probably after that we'll embark on electricity and magnetism.